So the last part of this workshop is our Encodings Showcase, where we are going to have several people, starting with Katalin, telling us about interesting stories about interest in encodings. So probably to save time, I will let people introduce themselves as they prefer. So please, Katalin.
Thank you. So my name is Katalin Fazekas, and I prepared here a few slides on our work with Markus Zinn, Armin Bire, and Sophie Parag. And we published this work last year at the CPAIOR conference. And basically, our goal was in that work to find a SAT encoding for sequence at most one constraints. And I just hope that you will find interesting our steps. So I would start just really quickly by showing how these constraints look like. If we assume that we have a sequence of, let's say, 15 Boolean variables, and we define a width of 5, then the sequence at post 1 constraint set in that configuration would be the conjunction of these 11 at most 1 constraints, where we can see that each of the constraints are talking about exactly 5 of the variables. And the easiest to imagine these constraints by if you have a window of width 5 and you slide it through your sequence of variables, and in each step you say that all the variables which are right now in the window, among them at most 1 can be true. Now, we originally called these constraint sets staircase at most 1 constraints, because if you realign them by the variables, then you can get this really nice shape of the stairs, but in this talk I will try to always call them sequence constraints, because this is how they were apparently introduced in the CP community several decades ago. But it's important that there it usually means a more general global constraint, while in our work we were really focusing just on this subcase where we talk about at most 1 constraints. And the reason why we wanted to encode these problems as SAT, because we wanted to solve the anti-bandwidth problem with the help of SAT solvers, which is basically a graph labeling max-min optimization problem. And unfortunately, I do not have the time to properly introduce it, but in our paper, you can find how encoding of this problem leads for several sequence constraints. So if we have this constraint set, we basically would like to find the truth assignment for each of the Boolean variables in it, such that all the constraints are satisfied. And of course, this is only one constraint in a bigger problem. So we have much more constraints on the same variables. And a straightforward solution for that problem would be just to simply use an off-the-shelf at most 1 encoding for each of the constraints. Like in SAT, we have several these kind of methods. And so this is how we tried at the very beginning. And soon we realized that the resulting formulas are just extremely large. So on that figure, you can see if we have, for example, 500 Boolean variables, then depending on the width of this window, which I mentioned, we can easily end up with more than 100,000 of clauses. And again, this is just one of our many constraints in the problem. So here on that figure, for example, this red line is the sequential counter encoding, or this dark red colored line is the pairwise naive encoding of each of the at most 1 constraints. And apparently this is the smallest what we can get up to a certain bit. And already here we get this size just by filtering out repetitions of pair constraints, because if we take a closer look on the constraints, we can see that they are continuously overlapping. So there is a really large level of syntactical sharing between the at most 1 constraints, and that was exactly what was motivating us for looking for other encodings where we could somehow exploit this sharing or overlapping between the constraints. So in our approach, we first tried to focus on the disjoint constraints in this constraint set. So we picked every 5th constraint, if we stay with this example, where then we will have for each variable will occur in only one of the atmos1 constraints, and all the variables will be in at least one of the constraints. So it's maybe easier if you put these selected window constraints next to each other, that basically we cover the whole sequence of variables with these selected constraints. And as a very first step, we just simply built a binary decision diagram for each of these selected atmos1 constraints. For this, we used a method which was introduced for pseudo-Boolean constraints in 2012. And one observation in this building step that the order of the decision variables in this BDD is basically implicitly determines how do we evaluate the sum on the left-hand side of the constraint. So it's basically the associativity of the addition. So in the very first step, we constructed this BDD for each of our selected window constraint. And as a second step, we continued and now built another BDD for the exact same constraints. And it sounds pretty wasteful that why would we encode once again something which we encoded just in the previous step. But a big difference is that in that step, we choose the exact opposite of the variable orderings. So if in the first step, the BDD was reading the sum from the left to the right, then in the second step, we read it now from the right to the left. And that's exactly why we actually call the encoding duplex encoding, because we encode the constraints twice. And so at that point, we have two BDDs for each of our selected disjoint atmos1 constraints. And then we just simply traverse these BDDs and transform them into CNF form. For this, again, there are already several methods in the literature. You can pick your favorite one, but what is an important side effect of that step is that for each subtree in these BDDs, then we will have a Boolean variable which basically refers on that part of the constraint. And that's exactly what we need in the last step, where we start to focus on all the other constraints, which we did not encode in that step, so the overlapping ones. Because for these constraints, we just apply a simple decomposition where we just split them up into two parts. And for example, here we have an atmos1 constraint from x8 till x12, and we say that, okay, there is one part of it which must fulfill the atmos1 constraint, and there is another part. And also we have to guarantee that at least one of the two parts must be atmos0. So this is just a very long way to say that the sum of these 5 variables can't be more than 1. But by using this long-phased description, we actually use only expressions which already occur in our previously built BDDs, where we already introduced Boolean variables to refer on these expressions. So actually, we can encode this atmos1 constraint only by 3 clauses, 2 unit and 1 binary clause. And that's actually the strength of the encoding, that the number of clauses here is completely independent from the length of the atmos1 constraints, because even if the width of the window would be 200, we would still need only 3 clauses to describe it. So these are the 4 steps of the encoding. If we put all of it together, then we can see that we selected these disjoint atmos1 constraints. We built 2 BDDs for each of them. Then we encoded them into conjunctive normal form. And then for all the remaining constraints, we just introduced 3 clauses to glue together the right parts of the built BDDs. And as a result of this encoding, now if we come back to the size comparison, then we can see that we end up indeed with a very, very small representation of the problem compared to any of the off-the-shelf SAT encodings. But on its own, it does not guarantee that the solver will like this formula. So we also try to use this encoding then to address the anti-bandwidth problem. And here you can see first just a few smaller graphs. As I said, it's an optimization problem and for graphs. So here we have the nodes and the edges of the graphs, and we compared 4 different approaches to find the optimal anti-bandwidth. So there was our SAT encoding, there was the state of the art, which was a MIP formalization of the problem, an iterative MIP formalization. And additionally, we considered 2 CP formalizations, but both of them were really naive encoding of the problem, once with Cplex and once with Minizinc. And already, so in these columns, we can see the best found solution for each of the approaches. And already on these smaller graphs, we can see that the SAT approach could find actually the best solutions in almost all of the cases. And the difference becomes obvious if we move on to the larger graphs, because here we can see that the naive CP approach could not scale at all, and while the MIP formalization could solve, could at least start to solve some of the problems, in most of these cases our approach could find a better solution. So just to sum it up with one sentence, the main steps of our encoding is that we encode some of these constraints twice with the hope that then we can maximize the structural sharing when it's about the other constraints. And as a result, we got a really short encoding for sequence at most one constraints. And this is actually in some cases even smaller than the CP approach. And here I had another point about the arc consistency of this encoding, which I will now leave out. And yeah, then we use this encoding to address the anti-bandwidth problem, and we found some nice solutions. So that was what I wanted to show you, and thank you very much for your attention.
Thank you so much. So what was the point about the arc consistency?
That depending on what CNF encoding we use on the BDDs, but in general, this unit propagation establishes the arc consistency, but now I'm not sure if it means the same for me as it means in the previous discussion. So I rather would not go there.
Okay, thank you. Questions, comments? This is really cool.
Thank you.
Okay, if there are no questions, let's move on. So, Said, please share your screen, and the floor is yours.
Yeah, sure. Let me share my screen. Can you see my screen?
Yeah, with everything on it.
Oh, sure. Okay.
Please.
Great. Should I go?
Yes, please.
Okay. So my name is Said Najati. I'm with AWS at the moment, but this work was done during my PhD with Professor Vijay Ganesh at University of Waterloo. And it's about doing cryptanalysis on cryptographic hash functions using SAT technology. So the problem that we wanted to look at was the algebraic fault attacks on specifically SHA1 hash functions. And the question is, given a hash output and some extra constraint that we could extract from injecting fault onto a hardware implementation of the hash function, find a message that hashes to that output. But I don't go into all the details of algebraic fault. I just want to focus on the core problem within that algebraic fault attack, which is the preimage attack. And simply stated, given a hash output, you need to find an X which hashes to that particular output. And the way we usually encode this problem into SAT is just encode the SHA1 hash function in CNF and then fix the output according to the value of H and solve the problem for X. To be able to encode the SHA1 hash function in CNF, we need to look inside the SHA1 and see how it looks like. So this is the architecture of a step function inside SHA1. It operates on a bunch of state variables, AIs, on the left, and it mixes in the values of these state variables, passes through some Boolean functions, and mixes in chunks of input, which are 32-bit chunks of input. And after that, it generates the next intermediate or state variable. And it goes on mixing in different chunks of input to arrive at the output from these state variables. And all of these state variables, chunks of input, these constants, all of them are 32-bit registers. And all of these functions are 32-bit bit vector functions. Here, f is a Boolean bitwise function, and these plus boxes are modular additions. And these thingies are bitwise rotations. So they don't change the bits, they just reorder the bits inside the register. And SHA1 actually repeatedly applies this function on the inputs and state variables to arrive at a hash digest at the end. So to also the f function in the middle could change based on the step that we are in. For the first 20 steps, the box is an if function. So it simply says if x, then y, else z. For the next 20 steps, the function f is 3-input XOR, and for the after that we use the majority 3-input majority, and the rest is again XOR. And I should mention that SHA1 does this 80 times, but it's solving for 80 steps is so hard that we solve a round reduced version, like more like 23, 22 steps instead of 80 steps. And now if we want to encode this function into CNF, we need to encode basing blocks in CNF and then connect all of these together via encoding of a circuit into SAT. For example, simply to encode the if function, because it's a bitwise function, for each of the output bits of function f, we say that we force it to be equivalent to the application of function if on the inputs. And we derive the CNF formulation of this equivalence. Similarly, we could do this for XOR function and majority function and arrive at these CNF formulas and concat all of these together to generate formulas for different steps. But these are the easier ones. The more complicated one is implementing the modular addition. And why is it more complicated? Because there are 5 things that are being added together, these elements, to arrive at the next intermediate value. So one way to encode this is simply to encode a 2-operand addition, 2-operand 32-bit wide adder, and then add 2 of these, then the result with the next one, result with the next one, and so on. But this gives you a very large encoding overall, and it would be harder for a SAT solver to solve. Another approach is to just encode directly a modular multi-operand addition. So in this scheme, you could see that, for example, we have 5 different bit vectors of x, y, z, t, and w. And in each column, we sum them up and find the sum and carry value. So if we sum up these 5 values, there are 5 bits, it gives us a value between 0 and 5. So it's small, at most 3 bits, which means that we have a sum bit and we have 2 carry bits that it carry to the next levels. And then if you look at the, so it means that each position receives at most 2 carry values because it could get a carry value from the previous column or the 2 previous columns. But at the end of the day, it becomes summing up 7 values, and still 7 bits sums up to 7, which is 111. It means that it doesn't exceed generating 2 carries. So one way to summing up this, like implementing this multi-operand addition, is that if we have a circuit to compute this 7 to 3 counter, which accepts as input 7 bits with the same weight, and generate a 3-bit value that represents how many ones are in those 7 bits. Then we could column by column sum up everything and chain all of these via carry signals. And in 2012, Nosum in his work implemented this 7 to 3 counter value using Espresso logic minimizer, logic optimizer, sorry. So it gave the truth table of this 7 to 3 counter into Espresso and got an encoding of how to implement this function instead of making it by hand. So Espresso gave a very compact encoding in terms of not generating any auxiliary variables. So it directly generated a bunch of clauses that produces the output. So in our work, we did an interesting observation. I was looking into seeing if I use Nosum's encoding, and if I set all of the bits at the input of a hash function, how many propagations the solver will do to arrive at the output bits. And surprisingly, I saw that when I set all of the input bits and give it to a stat solver, actually stat solver cannot derive all of the output bits only with unit propagation. So the information from the inputs of the function does not flow using unit propagation to the outputs of the function. And from the CSP literature and Karen's talk, we know that this has a name, and this is studied very well. And it means that the Nosum's encoding is not arc consistent, because there exists an implication at the higher level in the CP, like constraint definition level, that the unit propagation on this particular encoding cannot propagate. So it's not arc consistent. And here I could give a quick example if I have time.
You have 1 minute or so. Because
okay, so I could skip through the example and mention that generally there's this so for our work, there was this tension of having this small sized encoding and having an encoding that is good for propagation. This is exactly what Karen was also talking about. So ideal is to have a small encoding that has good propagation, like good. But our approach was that to keep the small encoding, the compact encoding that works very well with the SAT solver, but solve the deficiency of the unit propagation by extending the propagation programmatically. So we use the programmatic SAT architecture, which is inspired by CDCLT paradigm. And what it does is that the propagation callback analyzes the partial assignment and sees if there's anything set that implies something, but that implication was missed by unit propagation. And then at that point, the propagation callback will return a reason clause back to the unit propagation, and helps unit propagation strengthens it to actually imply the missed literal. So in other words, we could say that all of these constraints that we're implementing inside the propagation callback is a bunch of constraints that are implemented in C language, for example, because the SAT solver is, our SAT solver is written in C. And we could say that we went to generate an encoding which is a mix of CNF and C. And this is the overall architecture of where exactly the programmatic units lie in. And in our work, we extended both of the propagation and conflict analysis, but in this talk, we're more concerned about the programmatic propagation. And the architectural, it means that after unit propagation, if there's no conflict, programmatic propagation checks if there's any missing literal. And if so, it generates a reason clause and gives it back to unit propagation. And there's a tight loop between these two. Also, I need to mention that we focused on the relations on the input bits and output bits chunks of non-arc consistent part, which is mostly the multi-operand addition combined with the rotations of the inputs. And so because generalized arc consistency is a very strong property, we're not enforcing it on all of the intermediate and auxiliary variables, but we're enforcing it on the multi-operand addition part that is the main source of being not arc consistent inside the SHA1 encoding. So we kind of repair the broken chain from the input to the output. So we could kind of call it input-output arc consistent. And in some papers, it is called propagation complete, which means that if you have a Boolean function and you set something in the input of the Boolean function, it should propagate to the output.
Sorry, Sid, if you could go a little faster.
Yes, this is my last slide. So we implemented this in MapleSat, and this is the vanilla MapleSat on left, and the application of only programmatic propagation gave us this big boost on algebraic fault attack instances. Thank you.
Thank you so much, Said. So let's probably, for the sake of time, move questions to the end, because otherwise we are going to lose the audience. Sorry for that. Unless somebody has a quick, really immediate question while Stefan is setting up. Yeah, so this is very interesting that you could get those non-arc consistent encodings for SHA and things don't propagate. That's kind of unexpected. Okay, so let's then move on, and for sake of time, Stefan, please, the floor is all yours.
Thank you. I would like to talk about an approach where we have now actually a few papers with all these co-authors where we try out this approach on various problems. So the initial motivation was this: when I started working on SAT encodings a couple of years ago, it was a bit frustrating because all these nice instances from big data, etc., are quite large. And when you start with a SAT encoding, typically a SAT encoding is polynomial, but for some of these more complicated problems, the polynomial is of order 3 or 4. And even if a SAT solver can deal with millions of variables, which is in clauses, which is always which are great, and still when you first have this n to the 3 or n to the 4 blow up, then the actual instance size you can deal with is quite reduced. So there's quickly that if it's a graph problem with 60 to up to 100 nodes, you can do it, but then it's getting really tough. And therefore we had a couple of years ago this idea for this, we now call it SLIM, SAT-based local improvement method. We try to overcome this limit that we apply the encoding, the SAT encoding, or now we also do it with SMAC SAT encodings, to small parts of some initial solution that was computed by some heuristics. And then we use the SAT encoding to improve this solution locally. And we it's then a loop, and we improve, and often we just do it as long as we have time. Yes, the SLIM is also somehow related to the large neighborhood search meta heuristic, but if you really look at applications of LNS, they look quite differently to what we do with SLIM. So on a high scale, there might be some connection between these two methods, but I don't see this connection really in the individual applications. And here, that's this graphic of the SLIM loop. So the heuristic that we call the global solver provides us the initial solution. And then the local solver, which is often SAT or MAX-SAT, uses this initial solution to improve it over and over. And maybe there's a bit of terminology. Maybe let me just focus on the budget that we call like the size of the local part that we can work with. So for a graph problem, the local budget would be something like about 50 or so. There are 50 nodes of the graph that we can deal in the SAT encoding, but it varies. And the local timeout, that's the time we allow the SAT solver or MAX-SAT solver to solve this local instance. There it sometimes turns out to be not really good to give to bring the budget up to the limit and also this local timeout. Sometimes it turns out it's better to keep this value smaller than what we could actually do. And overall, it still outperforms an approach where we have larger budgets and larger local timeouts. And these are so far these 5 problems that we solved with the SLIM approach. And that's the first 3 problems are to compute certain decomposition for graphs. So branch width, tree width, and tree depth. For all 3, one must say also all share this general idea of SLIM. For each individual problem, one needs to solve certain problems because one has to fit in the new solution to the local problem to the global solution. And that this works, one has to solve some things specific to the problem at hand. So there's no like general black boxing where you can just throw your problem on and SLIM will solve it. And I will, together with Vaidyanathan, we will talk a little bit about the last one, the Bayesian network structure learning problem, and later Andre will talk about using SLIM to compute decision trees of low depth. And yeah, just briefly, what is this problem? So if we start at the right-hand side, we want to find a Bayesian network, which is basically a DAG, a directed acyclic graph, where we also, the nodes are also labeled with some tables, but we are interested in the structure in this DAG. And we want to find such a DAG using a score function, where basically for every node we have a potential parent sets. Each parent set gives us a different score. And the optimization problem is finding a DAG on these nodes such that the sum of all these scores are maximized. And so we have, and in addition, because later on we want to do Bayesian reasoning, probabilistic reasoning on this Bayesian network, we want that this Bayesian network has low tree widths. So we want to optimize the score subject to a certain bound on the tree widths. And so in other words, in MAX-SAT, we will have hard clauses for acyclicity, it should be a DAG, and bounded tree widths using a certain encoding for these 2 things. And it's actually partial MAX-SAT, as Maria Luisa already introduced, because we also have now soft clauses. And these soft clauses represent the scores of these different parent sets, and by optimizing the sum of the weights of these clauses, we can optimize the overall score. And now I have a little kind of animation. I'm happy that I can show it. We produced it for the III poster session, and yeah, there were not so many people around, so I'm happy that I can share it once more, but it's very quick. So assume this is the tree decomposition we get from the local solver. So it's heuristically computed Bayesian network, and this is the tree decomposition of it. Now, with a certain strategy, we select a subtree so that we keep within our budget. And then we form a local instance. So we basically collect all the nodes of the probabilistic variables that appear in this chosen local network. And now the aim is to find a new network for this red part and fit it back to the other parts. However, that this works, we need to make sure that these things will fit together. Therefore, we take from this boundary back certain edges and give the local instance additional virtual edges that the local instance will need to cover. And the other thing is we want to maintain acyclicity. If this new local solution is acyclic, it could still become cyclic by some directed path that's run through these gray external trees. So therefore, we look for directed cycles in these external trees. And if there is such a directed, or not directed cycles, directed path, if there is such a path, then we can represent this by we'll call it a virtual arc, which gives us an additional constraint the local solution needs to specify. And now, if we put all these things together, virtual edges, virtual arcs, we now get to this local instance, which is more constrained than a general Bayesian network structure learning instance. And now we can feed this into, with our MaxSat encoding, to our MaxSat solver, which produces a new instance, this green one. And because of these virtual edges, this then fits together with these subtrees that we put aside. And because of these virtual arcs, we can be sure that the solution will be acyclic. And now we repeat this selection until we come up with until we run out of time. So basically we can go on and on. Theoretically, there could be a limit where no additional improvement is not possible anymore, but in practice, you could go on for hours and you will always be able to improve. And it turns out that the speed of improvement is better than the speed of improvement when we apply these heuristics and run the heuristics for longer. But here I hand over to Vaidanathan, who will now talk a little bit.
You have about 1 minute left.
1 minute left. Okay, I think Vaidanathan, please continue.
Yeah, okay. Yeah, so I'll quickly go over the, am I audible? Can people hear me?
Yeah.
Sorry. Okay, yeah, so I'll quickly go over the experimental evaluation and what we learned from this. So basically these, for our experimental setup, we started with an initial solution that we got from this heuristic after 30 minutes. And at this point, we split into two parts and we run slim over the solution to obtain solution B. And we continue running the heuristic over the solution to obtain solution A. And comparing these two solutions by the BIC score metric, we saw that the slim solutions are significantly outperform the heuristic solutions. And what was worth noting here is that with small budget values of 10 and small timeout values of 2 seconds, we were able to maximize the performance. And our intuition is that we are able to get in multiple runs of this local improvement, and that matters more than getting more better quality runs. So in this case, quantity dominates quality. So this again is a quick plot of how with the smaller timeouts, you can see that there's more improvements, and the quality of improvements doesn't change that much between the different timeouts. And on the right, you can see a CDF plot of Kmax plus Slim, which is running Slim on top of Kmax versus just running Kmax alone. And the Slim version is significantly better at improving instances than just continuing to run Kmax after this 30-minute mark. And one last thing that I'd like to point out is, which we found really interesting, was that in many cases, this Slim version of the encoding, which is iteratively running over local parts to obtain the solution, was also much better than the one-shot version, which is in cases where the global instance is small enough to be encoded and solved practically by just a single sat encoding. The Slim version was much better, and the only drawback here being that we have no guarantee of optimality. And apart from that, we realize that the performance of the Slim version is much better because it's able to break up the problem into individual chunks and really focus on these smaller local chunks. So this is what we learned from our experiment with Slim, and Andre will continue with a different problem and a different perspective. So thank you.
Thank you so much. And please, Andre, Stefan, if you wouldn't mind stopping sharing if Andre is doing his own. By the way, just to say one thing, those are very short talk, and there is not enough time to do justice to anything of it. But my hope was that this would allow you to see a sneak preview of what kind of cool results people did, and maybe we could get together and arrange longer talks by the same people, kind of more directly and interactively rather than through workshops. Okay, Andre, please.
Maybe just, yeah, I will go briefly, but for 10 seconds, I want to make some advertisement for the seminar. So if any of the short talks interested you, write me, so then we can set up a seminar talk in the future. So since it's really late, I will keep this short, and I hope that Stefan and Vaidyanathan already convinced you that SAT-based local improvement is a good technique, and we applied it to decision tree learning, and we were able to greatly improve upon existing decision tree heuristics. What I want to highlight in the story is there was a state-of-the-art encoding for decision trees that performed best among those that were proposed. And there they assume a decision tree. So maybe briefly, so we tried to optimize the depth of the decision tree, so get depth minimal decision trees. And the best encoding that was known when we started this was an encoding that assumed a full binary tree with a given depth. So if you have depth d, the binary tree has 2 to the d many nodes. And this is and since you have to reference every node in the encoding, this is exponential in the depth. And we proposed a new encoding that was based on a different characterization of decision trees, on a partition-based characterization. And this encoding was linear in the depth, but quadratic in the number of samples. And usually you have a way greater number of samples than the depth. So in general case, our encoding was slower than the state-of-the-art encoding, but there were edge cases where our encoding was faster. So what we did is we tried to find the limits for both encodings in terms of the number of samples in the instance and the maximum depth. And then we used these limits when we selected our sub-instances so that we stay within the capabilities of the two encodings. And we also determined the kind of the threshold values when does which encoding perform best. So which are kind of the edge cases for which our encoding performs better. And then we created a hybrid encoding that chooses which of the two encodings to use based on this data. So how deep is the tree that we try to optimize, and how many samples do we have? And so the result is that if we use this hybrid encoding, we can decrease the depth by 34% on average, compared to using only one encoding. And since the instances we used vary greatly in the size and in the depth of the tree, this means that the gains are vastly larger for many instances and very little for other instances. And Slim worked generally very well on this problem, so we were able to improve almost all the instances. So my takeaway from this is that it's even if you have multiple encodings and there is a clear best encoding, it may pay off to look into the edge cases for which other encodings may perform better, and then if you can statically choose, use multiple encodings. And the second story I want to briefly mention is, so this is an ongoing work, so it will be a little bit more abstract. But basically, it's a graph decomposition encoding we worked on, and it's based on elimination ordering. So you have a linear ordering, and you eliminate nodes according to this ordering, where elimination is defined by the problem at hand. And usually you do this in an implicit way. Yeah, so encode which node is eliminated before which other node, but you don't encode this is the first node, this is the second node, this is the third node, because using this implicit method, you can take 2 out of n, where n is the number of nodes, many variables, and you only need constraints for transitivity. But our encoding ended up to use number of nodes to the 4th many clauses. Then we thought a little bit more about it, and then we found out, if in this case, if we encode the ordering explicitly, so we really encode this is the first node to be eliminated, this is the second one, and so on, we can do this in cubically many clauses. And this introduces some symmetries that are not existent in the first encoding. And the ordering part is a bit larger, but then the checking constraints, we need way fewer checking constraints. And how big is the difference? So on a graph with 75 nodes, which was the biggest instance that could be solved by the first encoding, it requires 30 million node clauses and 2.5 million variables and takes about 2 hours to solve. And the second encoding takes only 2.5 million clauses and 0.3 million variables, but is not able to solve the instance optimally within 8 hours. And even on a smaller instance with only 15 nodes, the second encoding fails. So it's not news that investing some size into symmetry breaking pays off usually, but for me, the extent of this, like 30 million compared to 2.5 million clauses, is a huge gap, was very surprising, and I thought that may be an interesting story to share for this talk. So with this, I'm done.
Well, thank you so much. And thank you everybody for the wonderful stories. Sorry for running over time. Other quick questions, or should we take it to GatherTown? Or maybe I'll post the link to GatherTown in the meantime, if anybody has questions.
I have a short one. Could one use SLIM to re-encode the CNF formula such that model counting would become easier? Or did I misunderstand something?
Stefan? I have no immediate thoughts on that. I would have to think about this.
The question once more, whether we can do what?
Could one take a CNF formula and use SLIM on it such that the model counting would become easier? So the trees should become smaller, no?
Yes, that you can do, yes. Actually, we are also working on something because the tree bits is not, if you have not only binary variables in your Bayesian network, then tree bits is a bit of a very coarse measurement, because it matters whether you have a binary variable or a variable of domain size 10. And so one could formulate a more fine-grained measurement than tree bits. And we have already some preliminary results that with SLIM we can quite easily encode such constraints, and so it is quite versatile to apply SLIM in this setting.
Yeah, okay, but you would not usually start from a CNF, or doesn't
no,
it matter?
we don't from a CNF. No, we start from the DAG produced by the heuristics, because we are working here with about up to 4,000 probabilistic variables. So it's a huge instance, and there are heuristics who give us within seconds a heuristically computed Bayesian network. And then SLIM starts selecting subnetworks and improving the score there without worsening the tree width bound.
Okay, thank you.
Okay, any more questions, comments? This was such a great session. Thank you so much, everybody who spoke and everybody who asked questions. If not, then let's call it a workshop and see you at Gather Town. And thank you so much.